Welcome to the Temporal Graph reading group today, everyone. And nice to see you back for the talk. So we are very glad to host Lianghao Xia from the University of Hong Kong today. And I will start with the speaker introduction, and he will be presenting the AnyGraph graph foundation model in the wild paper in their recent work. So Dr. Xia Lianghao is currently a postdoc researcher at the Data Intelligence Lab of the University of Hong Kong, in collaboration with Professor Huang Chao. And Lianghao's research mainly focused on the field of data science with a particular focus to foundation models, graph learning, information retrieval, and spatial temporal modeling. And he has published 14 first author papers in top conferences in the related field, and he has received multiple awards, including Most Influential Paper Award at the Web Conference of 2023, in SIGGRAPH 2023 and 2022, as well as Best Paper nominations and Spotlight Paper Award at the Web Conference. And he was also selected by Stanford University as the world's top 2% scientist in 2024. So with the introduction, I will hand the mic to you, Lianghao, and thanks for your presentation.
Okay, thank you for the introduction. So I will share my screen. Okay, can you see my screen?
Yes, and do you prefer the questions from the audience to be in the like in the middle of your talk or at the end of your talk?
Uh, I think middle of the talk is okay.
Okay, sounds good.
So can you see the slides now?
Yes, we can see the slides.
Okay, thank you. So let's begin. So hello everyone. I'm very glad to be here today. My name is Lianghao Xia. I am currently a postdoc fellow at the University of Hong Kong. Today, I will share with you about our explorations about graph foundation models, and I will introduce one of our most recent paper, AnyGraph graph foundation model in the wild. So as many of you may be very familiar with, graph is a very general form of language to describe and analyze entities with relations and interactions. So for example, we can have social graphs between people to reflect their relations, such as co-workers or friends or families. And we can also have transportation graphs to represent the relations between some point of interest in an urban space. And we can also have academic graphs, which may record relations between authors or relations between authors and papers. And also in the field of biological informatics, we can have some graphs to represent the relations between proteins or the relations between proteins and genes or some disease. And also we have communication graphs representing the connections between some devices, and we can also use the graph structure to represent some real-world knowledge known as the knowledge graphs. So for all of these graphs, the current most representative learning paradigm is called graph representation learning. We can first take the input graph, which consists of nodes and edges between them, and use some kinds of machine learning models to learn some representations for the nodes. And these representations are known as the node embeddings. The key factor of these embeddings is that they can preserve the graph structures. For example, we can use some similarity functions between two node embeddings to evaluate the connections between the nodes in the original graph. So for graph representation learning, here are some representative works. For example, we have the graph neural networks, such as graph convolutional networks. This method mainly conducts some information propagation and aggregation to refine the node embeddings to better reflect the local connections between the central nodes. And also recently, there are some paper to address the generalization ability of to improve the generalization ability of graph neural networks, known as the self-supervised graph learning methods or the pre-training graph learning methods. This method will apply some pre-training tasks for the graph learning models to learn representations without some sufficient number of labels, maybe. And these pre-trained representations for the nodes can be used for downstream applications to increase their performance. And although there have been so many works on graph learning, one key limitation still exists, that is the generalization ability of these models. For example, if we want one graph model trained on graph A to be transferred to be used on graph B, there are many challenges. For example, graph A may be a graph data on academic graphs, so it may contain nodes like paper, authors, and conferences. And also the relations may contain citations, citing relations or co-author relations, or a paper published in a conference. But if we want to apply a model trained for graph A to another graph, which is a recommendation graph, the recommendation graph B may contain nodes like products and users and like some restaurants or other venues. And the relations contain purchase, add to cart, add to favorites, or other review relations. So the model trained on graph A must contain a lot of parameters, a lot of learnable parameters that is customized to nodes like papers, authors, and conferences. And it is really hard to transfer these parameters to represent some information for the products nodes or user nodes. So that is the generalization problem of graph learning. So here we want to propose a graph foundation model, which input the graph data of any domain or any data sets and can be used to handle different downstream tasks and downstream data. So that is what we want to do with graph foundation models. And there have been some works in this direction. A representative line is called graph language models. As we all know, large language models have shown its very strong generalization abilities in many tasks, in many different tasks. So we wonder if the large language models can be used to unify the different kinds of and different domains of graphs in the field of graph learning. So representative works including one for all and zero-G. And in our group, we also have done one of these work, which is known as Graph GPT, Graph Instruction Tuning for Large Language Models. This paper proposes to utilize a large language model as the graph foundation model to make like zero-shot predictions with graph data. So here are some key points about this paper. It enhances the LLM with the graph tokenizer. And also it proposes several different graph instruction tuning tasks to tune the LLM to be able to handle graph data. So first of all, it's the first challenge it faces is that how can we feed graph structures into LLMs? LLMs are only able to handle language data, text data, but graph cannot be directly and easily translated into text to be understandable by LLMs. So in this paper, they it proposes to transform graph into a sequence of graph tokens. The so-called graph tokens is essentially a sequence of graph embeddings representing the semantics of different graph structures, such as nodes and subgraphs. And by applying some alignment methods, we can let LLM to understand these messages. And so it firstly conducts a text graph grounding phase. It's initializing the graph encoder, which is utilized as the graph tokenizer with the natural language alignments. So in this way, we can let the embeddings generated by the graph encoders to map with the embeddings of the language models. So the second problem is how to let LLM understand the graph prediction task and let it to conduct a good enough performance on the graph learning tasks. So for this purpose, it proposes first of all, it proposes a self-supervised instruction tuning method. It lets LLM to match the graph tokens with the corresponding natural language content in the prompts. And it first proposed some self-supervised instruction tuning methods, and then it proposes some task-specific instruction tuning methods, such as the node classification task. So in this way, it can let the LLM to understand the graph tokens, and then it can let LLM to make predictions for the graph learning tasks. And then to enhance the performance, this paper also proposes another chain of thought method to distill the reasoning capabilities from larger and more powerful models, such as GPT-4 to the Graph GPT model. So although these graph language models have proposed some solutions to the generalization problem of graph learning models, but they can only handle token set shift with LLMs for text-based data, which is known as the text-attributed graphs. But what if the graphs are without text? There are no text. So this is the first problem. This method cannot handle textless scenarios. And second problem of this method is that it's really hard to learn the different patterns of graph structures across different data sets. For example, in a recommendation graph, we may have very noisy graph structures. The users may randomly click some items, and so the graph structures are with a high percent of noisy edges. But for other graphs, such as the academic graphs, every edge in the graph represents solid relations between authors and papers. So the graphs from different domains are really different in structure patterns. How can the graph foundation model to handle such structure shifts is another problem for graph foundation models. So to deal with these challenges, we propose another work in this field, which is called OpenGraph towards graph foundation models. This paper has been accepted by EMLP of this year. So a spotlight of this paper is that it tries to distill generalization ability from the large language models. And also you can see the QR code for the archive paper, for the code, and for another report of this paper. So in this paper, we try to solve the zero-shot graph generalization across different graphs. For example, OpenGraph is required to be pre-trained on a recommendation graph, and then it is asked to predict for medicine, disease, and gene relations. And the most challenging part about this task is that there is no overlapping nodes and features across different the source graph and the target graph. So this is the first challenge we faces, which we name as token set shift across different graphs. The token set here refers to the elementary um, elements in the graphs, such as nodes and features, which we can assign model parameters to. So to solve this problem, we propose a unified graph tokenizer, which is based on a unified SVD-based representation mapping. So we use SVD to project the adjacency matrix of the input graphs into a N by D matrix of the nodes representations. And we also call these representations as graph tokens. They are essentially untrainable representations for the nodes. Although these nodes are untrainable, but we use SVD method as an untraining method to try to preserve the original information about the adjacency matrix. And also in this part, we conduct feature augmentation. We try to conduct high order graph convolutional smoothing to capture the high order connectivity in the original graph. And also in this way, we can make the adjacency matrix from sparse matrix to a dense matrix, which is beneficial for the performance. So with this unified graph tokenizer, we project the adjacency matrix of any graph data into node embedding sequences. And in this way, we can then utilize some methods like graph transformer, like transformer model, to learn the correlations between these nodes and refine the node embeddings for these nodes to make accurate predictions. So here we also faces another minor issue, which is the efficiency of the graph of the transformer architecture. As we all know, transformer is a very heavy model. It learns and pairwise relations between all the tokens in the sequence. But for a graph model, we may contain a very large amount of nodes. So to deal with such long sequences, we propose an efficient, scalable graph transformer architecture. We shorten the length of the sequence by sampling only the current training batch nodes. And also we don't learn pairwise relations of any node pairs. Instead, we randomly select some anchor nodes and learn the relations between all the vanilla nodes with the anchor nodes. So in this way, we can use a low rank technique to avoid calculating too many relations between the nodes. And also, there is another challenge, which is the domain-specific data scarcity. For example, if we want to train a model for recommendation graph, but we don't have enough data information about this domain, so how can we generate this domain-specific data to better train the OpenGraph model? So to address this challenge, we propose to distill the word knowledge from the large language models. So specifically, we use LLM to generate some graph data of a specific domain. And then we use these generated graphs to train OpenGraph to enhance its training. The process of these generation processes can be divided into three parts. The first one is to generate the nodes. And the second one is to generate edges between these nodes using the semantics of these nodes. And the third phase is to just refine the generation results. So specifically for the node generation process, we first come up with some descriptions, text descriptions about this target domain or target scenario, and the most general entity name for the nodes in this domain. For example, if we want to generate products in a recommender system, so we have the like scenario description, which is e-commerce platform like Amazon. And we also can come up with some most general entity names, such as products. And we prompt LLM to divide this general entity into subcategories with a finer granularity. So the LLM will answer with clothing, electronics, shows healthcare, or baby, or so on. And we continue this process iteratively. We can finally get some specific enough descriptions about the entities, which can well represent some real-world products of recommender systems, such as white hooded sweaters, men's clothing, shorts, golf shorts, and so on. And the good thing about this method is that during this process, we can also get a text description about these generated entities. And we can use these descriptions to generate the relations between them. So we have this text descriptions for each node, and we can generate the textual embeddings for them, and we can use this embedding to calculate the relations between each two nodes, and we can use this relation to estimate the probability of one node connecting to another node. And with this probability, we utilize skip sampling to generate the edges of these graph datasets, and we can use it to train our model. And one thing need to be attention is that OpenGraph is trained with only synthetic graph, but tested on real datasets. So as you can see in this table, OpenGraph achieves superior zero-shot prediction capabilities compared to the zero-shot performance, compared to the few-shot performance of the baseline methods. And we can also see that there are some baselines of pre-training methods, but they do not always perform better than the simply end-to-end training methods. This also reflects the difficulty of transferring the trained knowledge from one graph dataset to another graph datasets. And also we conduct some ablation studies to evaluate the effectiveness of graph tokenizer and our graph generation process. And also, we can see that here, our generated datasets, by using them as the training datasets, actually generates better performance than using real-world datasets as the pre-training datasets, which also reflect the effectiveness of our dataset generation process. So the second work we do in this research line is AnyGraph, graph foundation model in the whale. And there are also the QR code for our GitHub project and the paper. So in this paper, we want to train a graph foundation model, which is usable for any graph from any domains with only one pre-trained model. So in this paper, we try to address four challenges. The first one is structure heterogeneity. As we mentioned earlier, different domains may have very different graph data. Some graph data may be dense, and some may be sparse. Some may be noisy, and some may be contain very solid edges. So how to use one model to tackle all of these heterogeneous features or characteristics of graphs is a very challenging problem. So the second challenge we face is the feature heterogeneity. As we all know, different datasets may use very different features with even different dimensionality. For example, some datasets may use numerical features for the nodes, and some may use some textual features, and some may use bag of words, some may use text embeddings, and there are also categorical features. And how to let one model to handle different types of features is a very challenging problem. And the third challenge we face is the fast adaptation. we want the foundation model to efficiently adapt to new graph domains. So instead of only relying on the pre-trained capabilities on different graphs, we also want the model to be fastly adapted to different domains. And the first one is that we try to explore whether the scaling law applies to the graph foundation models. So specifically, we expect the performance to scale with the amount of data and model parameters. And overall, we adopt MOE architecture for the AnyGraph model. It contains multiple experts instead of only one trainable model. And we expect different experts to handle one type of graph data or several types of graph data. So in this way, we can better handle the heterogeneity issues about the cross-domain graph datasets. And for each expert models, we designed adaptive and efficient graph expert architecture. And also we apply some efficient cross-domain model training techniques to train our model. So specifically for our MOE architecture, it contains several different experts. And as we mentioned, each expert is expected to handle only one type of graphs or several types of graph, not all of the graphs. So in this way, we can expect the different expert models can focus on just some graphs with specific characteristics. And then we have a very crucial problem, which is how can we decide which expert to handle which graphs? So in this, here we designed an experts routing mechanism, which is responsible for assigning competent experts to the input graph models, graph data. So specifically, this routing mechanism is based on self-supervised learning laws for graph data. And also we use these laws to let different experts to do some tests on the input graph. And we evaluate the loss of these experts on the input graphs. And we select the expert model with the smallest or with the minimal loss to assign it to the input graph for training and for testing. And although this method is empirically very good, it's actually empirically it's always achieves the best assignments, but it causes a suboptimal scenario, which is some very few expert models are assigned to mostly all of the training graphs. So in this manner, most expert models are actually not very well trained. So this causes the expert models to be a waste. And we, to address this issue, we propose another frequency regularization, which is basically assigning, give more opportunities to the expert models with less training experiences. So there is an ablation study which also evaluate the effectiveness of the MOE architecture and the frequency regularization.
Just a quick clarification question.
Yeah.
So how do you train the experts? Are the experts trained on specific domains? Like they only see specific domains, or they train like cross domains as well?
Yeah, actually they are not trained specifically or explicitly for a specific domain. We will mention actually all the training graphs are randomly shuffled, and we use the routing mechanism to assign experts to input graphs for both training and evaluation. So during the training phase, these experts are assigned to the input graphs which they are more competitive as. Yeah.
I see.
So in this way, we expect the expert models to perform better and better on specific types of graphs. Yeah, and there is a very specific case study on the routing results about our routing mechanism. For example, this is the dimension for the expert models, and this is dimension for the datasets. And we can see archive, TA, photo, Goodreads, fitness, and these datasets are assigned to mostly very similar expert models. And actually, these datasets share the same feature spaces. So, and also for Movilance 1 million and Movilance 10 million, these two model datasets are actually from the same source, both from the Movilance platform, and they are assigned to very similar expert models. And these datasets are the training datasets. And this also applies for the testing evaluation datasets. YOP-T, STEAM-T, and Amazon-T utilize the same feature space. And we can see the similar set of expert models are used to handle these datasets. So the second part of AnyGraph is how we design the graph expert models. So actually, we want the graph expert models to address the in-domain graph heterogeneity issues. That is, we don't expect it to handle like different feature spaces, but it needs to handle some elementary challenges such as changing dimensionality or changing orders of the nodes. So first, we also apply the SVD-based unification process. But in this paper, we not only unify the representations for the adjacency matrix, we also use SVD to unify the feature spaces, the node features. We found out that we can also use SVD to decompose the feature matrix of the nodes into some latent representations. And we can then get like N by D matrix for the different features matrix. So in this way, we can unify the dimensionality of the feature matrix. And also, SVD follows a specific pattern to do the decomposition work. So we can also expect the resulting resulting matrix to follow some patterns which can be handled by the later learnable parts. And after this unification process, we also conduct some high-order connectivity injection with graph convolutional networks, but this GCN network is untrained without parameters. And then we apply a feature encoder, which is trainable. But in this paper, we don't use transformer because transformer is too heavy for a small expert model. Instead, we use a simple, very efficient and strong MLP network to do the work. It is mainly composed of some simple transformation, bias, and activation, and dropout, and layer norm. And we found out actually this simple design works very well as a small graph expert models. So for the training part, we first pre-process some information to accelerate the training speed. We pre-process the initial representations for all the nodes, and we also pre-calculate the routing mechanism between the expert models and the datasets. So we input this pre-processed information into the training process. We use cross entropy as our training objective loss, and we periodically reconduct the decomposition process, the process of the initial representations, and we also periodically conduct the expert routing, which contains some structure augmentation process. So in this way, we can enhance our training data with from the aspect of features and structures. And also there is a ablation study which we evaluate the performance of removing the augmentation, and it exhibits a very clear decline in the zero-shot performance. But one interesting thing about this is that actually removing the augmentation causes some performance increments in some cases, but for the full-shot performance, which means the augmentation may hinder the supervised learning performance in some cases, but it eventually enhances the zero-shot generalization abilities for the model. So for the evaluation about this model, we utilize 38 different datasets for our training and testing. These datasets cover a very wide range of domains, including e-commerce, academic networks, biological information, email networks, website networks, trust network, and role networks. And you can refer to our paper for specific information about these datasets. And to better evaluate the models with many datasets instead of one by one datasets. So we divide the datasets into multiple groups. Essentially we divide them into two groups. These groups are non-overlapping in data sources and feature construction methods. So we are making the two groups very different from each other. So we can train on the first group and test on the second group, but the model has not seen the same data source or the same data node feature construction methods. And also we divide the data sets into different groups by their domains, including the e-commerce datasets, academic datasets, and other datasets, including some bioinformatic datasets and other small datasets like neural networks and web networks and so on. So also we conduct node classification. There are 5 node classification datasets. And we also we compare the zero-shot performance of AnyGraph with the few-shot performance of the existing methods. And we can also observe the cross-domain generalization ability of AnyGraph compared to the baseline methods. So also in this work, we compare AnyGraph to the 2 other graph foundation models proposed by our group, GraphGPT and OpenGraph. And we can see that AnyGraph actually outperforms these 2 models on multi-dataset evaluations. So this also reflects that AnyGraph is better in handling more diverse datasets compared to the previous graph foundation models. And also here we conduct another ablation study. We remove the utilization of the node features, and we can see a performance decline for AnyGraph. And also there is another removing the features ablation study, and we can also observe the decline, which verifies the effectiveness of using SVD as a unification method to handle different types of graph features. So we also test if the scaling law applies to our AnyGraph as a graph foundation models. We tune the number of model parameters and the number of training samples from less to more, and we evaluate the performance. We mainly evaluate the zero-shot performance to see if the generalization ability applies to the scaling law. And we can see that with the increase of model parameters and the number of training samples, the performance continues to grow with this model size. But for the full-shot performance means that if we train on graph datasets such as Yelp datasets, we also test it on the test set of the Yelp datasets. So here the generalization, it has a lower requirement for the model's generalization ability. It only needs to handle the seen datasets, but the unseen part of it. So we can see that for full-shot performance, it actually stops to increase at a very early stage. And this also gives us an insight. If we want to explore the scaling law or stronger performance or stronger capabilities of a model, we can test it. We can do some research on its more difficult tasks instead of the simple ones like the functional performance of graph learning. So also we can observe some emergence abilities of the AnyGraph. We can see the curves sometimes show a certain significant improvements in some points. This also implies the emergence abilities of AnyGraph. And also we can observe that for the increments of the training samples, it sometimes causes performance decline, but with more data sets, this problem will be solved. We think this phenomenon is due to that with less data sets, the model is can more easily to overfit some training data to cause the performance decline. But with sufficiently number of data sets, this issue can be solved by enhancing the model robustness. And also we evaluate the efficiency of the model. We evaluate the per epoch training time, and we can see that actually AnyGraph is very efficient in training. And also we can see that if we use the pre-trained models to fine-tune it on another data sets, and AnyGraph can actually achieve better performance with a faster speed. And this is the page about our group's GitHub, and we want to share with you our open source research papers. And if you are interested, you are welcome to check out our GitHub repo. And also, these are we make some article covers for our papers. If you are interested, you are welcome to check the GitHub. And thank you for that. That's all for my talk.
Yeah, so thank you so much for the talk. It's very clear, and I do have some questions, but I guess I will go after the audience questions. So we have a question from Kiarash. If you have the mic, do you want to ask the question yourself?
Yeah, so hello everyone. I have three questions, but let me start with the first one. So the first is, did you like compare this method with the soda graph method like in each task, because you're performing like you're evaluating your method on three different tasks, like graph level, node level, and edge level. I see like you have some zero shots, GIN, GNN, and two other methods, but did you also compare this with some soda? So this is my first question.
Yeah, actually, we compare our methods on with the sorts of general graph models like uh, different kinds of GNs and some different kinds of self-supervised methods or pre-training methods for graph learning. So, for example, if we contain some, if we use some datasets like spatial temporal or urban dataset, we didn't compare the performance to some urban computing methods like that. We just compare to some SOTA methods in general graph learning.
Oh. And all the methods that you compare with was in in few shot training, no full training. Like you didn't compare
Yes.
any graph with a
Yes.
full trained single model.
Yes. Actually, you can see also in these results. Actually, if you fine tune, for example, our AnyGraph, it will increase a lot. So, which means the functional performance actually is very high compared to just the zero shot performance at this point.
I see. Thanks.
And we think this is a actually very natural phenomenon because you don't even see any nodes of these datasets.
Right. Do you think by fine-tuning the AnyGraph model sufficiently, it's possible to beat the single model state-of-the-art on each of the data set? Or do you think there will still be some
I think at
differences?
least in our graph, our experiments, it works. For example, if you compare, this line is AnyGraph fine-tuning, and this line is GCN training end-to-end, and you can see there is a large performance gap. And even for this dataset, the gap is smaller, but there is also maybe an advantage for AnyGraph compared to both GN end-to-end training and fine-tuning graph scale.
Mhm. Do you have more questions, Kirash?
Yes, so another question is the training task here in AnyGraph is link prediction. Yes, for all the
Yes.
experts. So all the experts perform the same task.
Uh, yeah, for evaluating link prediction, all the methods are trained and tested for link prediction. Yes.
No, my question is like you train them all on link prediction and then evaluate the link prediction model on different tasks, or you train like any graph for link prediction, then other any graph for node classification. So I just want to.
AnyGraph is trained only for link prediction, but
Mhm.
the baseline models may be trained. For example, if we evaluate them on node classification, we train them on node classification.
I see. And all the experts are on the same task. So that was my question. And my last question is how do you know, like in zero shot inference, which experts should you use for?
We just use the routing mechanism. We can get the graph structures of the input graph, and we do some self-supervised predictions using all the experts, and we see which experts has the minimal loss, and we decide these experts will handle this input graph.
Okay, thanks.
Thank you.
Yeah, so thanks for answering the questions. I have a few more like follow-up questions, but for anyone in the audience, if you would like to ask more questions, feel free to type in the chat as well. So thanks again for the very nice work. I just want to ask, so your model is required to do SVD for any of the test set as well, right? Because you need to put in the
Yes.
features into the embedding space, the SVD embedding space, right?
Yes.
So do you
Yes.
have some issues with scalability for the SVD on the very large graphs and so?
At least in our data experiments, SVD is able to handle like graphs with tens of thousands or
Okay.
close to hundreds of thousands nodes.
Mm-hmm.
So I think it's okay for this. Empirically, I think if we are handling larger graphs, then maybe we need to do some sampling on the graph structures to
Right,
make it smaller.
right. That makes sense. Um, and another thing is that, so I think you are basically using the SVD as positional encoding to your experts, right? It's like very similar to what people do in graph transformers, and you take the Laplacian, like the eigenvectors and so on, right? Um,
Uh,
so
yeah.
so that's also limited because the different SVDs, depending on
Mhm.
the rank you select, there are some graph structure you cannot differentiate based on, what's
Yes,
the
yes.
embedding dimension, right?
Yes.
Um,
The SVD part is actually a projection from a larger space to a smaller space.
mhm.
So it's you cannot expect no loss in information in all cases.
Right, right.
So
Yeah.
yeah.
And have you tried with just taking the SVDs that you tried and feeding it to one graph transformer? So
Mhm.
like basically not using the MLP. So you mentioned that the computational cost is a constraint, right? But
Mhm.
assuming that
Mhm.
you are able to train the transformer just on all these SVD tokens, for example, and then you don't
Yeah.
necessarily need to have wiring mechanism to pick which MLP to use, right?
Sorry, I didn't get.
Uh, so
Sorry, I
so
don't.
So, so I think that maybe it's also possible to just take the features that you have produced from the SVD and just train a
Yes.
single transformer instead of a group of experts as you've done. But I do agree
Uh,
that the group of experts are more
yes.
efficient and much
Yes,
faster.
that is actually that is very close to OpenGraph. but we also do some graph generation in that work.
Okay, sounds good. Yeah, so that's all the questions from my end. If there's no questions from the audience, we can wrap up the talk here. And let's. Oh yeah, so there's more question. Yes, feel free to unmute yourself.
So just one question about the SVD, right? So the embeddings are created based on the SVD, but as Andy said, normally they use the eigenvectors about the Laplacian matrix. But in that case, the eigenvectors have a little bit more math background that support this. So, for example, the feeder vector of the Laplacian have some stochastic properties that uh, gives this a strong mathematical basis. But as you
Yes.
are using SVD on the adjacency matrix, I don't know if such properties they keep giving us information, right? Because, for example, the SVD decomposition, you have the left a space that is the U eigenspace, let's say, and the V eigenspace. So we have two spaces. One is the row vector space, and the other the column vector space. How the mathematics in these cases you are giving this a strong background.
Yeah. Actually, as you mentioned, using SVD has its very strong some math basis, but actually here we want just find another projection method from graph space to some dense representation space. So we can also use another different methods for this part. And for you mentioned the row vectors and column vectors. For example, here we just concatenate all of them to make all information visible to the later learnable part to just make an end-to-end training. We don't want to spend much efforts on designing the projection methods. Just use something that works, I think.
So great. Thank you, Lian.
Thank you.
Yeah, and thanks for the question. And thanks for the very interesting approach. That's very different from GNNs and graph transformers, and it shows like very good performance. So, definitely super interesting. And if you would like to share the slides, like you can also send me on the email. Then
Okay, great.
then I think that will be easier for people to get a QR code like after the talk. Yeah.
Okay, great.
Okay. Thank you. Have a nice day,
Thank you.
everyone. Yeah.
Have a nice day.
Bye. Thank you.
Bye.